There is a place in the universe where everything we understand begins to fall apart. Not slowly, not gently, but absolutely, as though the rules that govern reality simply stop applying. It is not a place anyone has ever visited. It is not a place any instrument has ever directly observed. And yet, scientists are remarkably confident that it exists because the mathematics that describe the universe demand it. A black hole is not truly a hole. It is not empty space. It is not a tunnel, and it is not a doorway to somewhere else. A black hole is what remains when matter has been compressed so violently that its gravitational pull becomes inescapable. Light cannot leave it. Time behaves differently near it. And at its center, according to the equations that have guided physics for more than a century, something happens that no living theory can fully explain. For most of human history, black holes did not exist in our understanding of the cosmos. The stars were lights. The planets were wanderers. The universe was vast, but ultimately mechanical, a place where it moved according to knowable forces. It was only when Albert Einstein published his general theory of relativity in 1915 that the possibility of such extreme objects entered the conversation. His equations described how mass warps the fabric of space-time, bending the paths of light and altering the passage of time itself. And within those equations, buried inside the mathematics, was a troubling prediction. If enough mass were concentrated into a small enough region, space-time would curve so steeply that nothing, not even light, traveling at 300,000 kilometers per second could climb back out. Einstein himself was uneasy with this prediction. He did not believe nature would allow such an object to form. For decades, many physicists agreed. The idea seemed too extreme, too alien, too incompatible with the orderly universe they believed they inhabited. But the universe, as it often does, proved stranger than human comfort preferred. Today, scientists know that black holes are not rare. They are not exotic accidents scattered across an otherwise predictable cosmos. They are fundamental to the architecture of the universe. Every large galaxy appears to harbor a supermassive black hole at its center, an object containing millions or even billions of times the mass of our sun, sitting quietly at the gravitational heart of hundreds of billions of stars. The Milky Way itself carries one. It is called Sagittarius A star, and it contains roughly 4 Messian solar masses compressed into a region smaller than the orbit of Mercury. Beyond these giants, smaller black holes are scattered throughout galaxies, the remnants of massive stars that exhausted their fuel and collapsed under their own gravity. These stellar mass black holes, typically between 5 and 50 times the mass of the Sun, are born in some of the most violent events the universe produces. And yet, once formed, they are among the quietest objects in existence. They do not shine. They do not announce themselves. They are known only by the effect they have on the matter and light around them. This is the paradox that makes black holes so deeply fascinating. They are simultaneously among the most powerful and the most silent objects in nature. They shape galaxies. They bend light across billions of kilometers. They slow the passage of time in ways that challenge everyday intuition. And yet, their interiors remain hidden, sealed, behind a boundary from which no information escapes. That boundary is called the event horizon. It is not a surface. It is not a wall. It is a mathematical threshold, the point beyond which the velocity required to escape exceeds the speed of light. Anything that crosses the event horizon, whether a particle of dust, a beam of light, or an entire star, moves inward from that moment forward. There is no turning back. There is no signal that can be sent outward. Whatever happens beyond the event horizon stays beyond the event horizon. And this simple fact has created one of the most profound scientific mysteries of our time. What happens inside? The question sounds simple, but it reaches into the deepest foundations of physics, touching general relativity, quantum mechanics, thermodynamics, and information theory. It has occupied some of the most brilliant minds of the past century, from Einstein to Stephen Hawking to Roger Penrose. It has generated Nobel Prizes, fierce academic debates, and theoretical proposals so strange they would feel at home in science fiction. And after all of that effort, the question remains open. Tonight, we will follow that question wherever it leads. We will begin with the death of a star and the birth of a black hole. We will approach the event horizon and examine what physics predicts for anything that crosses it. We will descend into the warped geometry of space-time, where time itself curves toward an ending, and we will confront the singularity, the point at which the known laws of physics silently break down. Along the way, we will explore what scientists have actually observed, what remains purely theoretical, and where the boundary between knowledge and mystery currently lies. There will be no exaggeration, no dramatization, only the science as it stands, patient, honest, and filled with a quiet wonder that needs no embellishment. Because the truth about black holes is already extraordinary enough. To understand what happens inside a black hole, it helps to understand how one is born. And the birth of a black hole is, in almost every case, the death of something else, a star, massive and luminous, that has burned through the last of its fuel and reached the end of a process that held it together for millions of years. Stars are not permanent. They appear that way from the surface of the Earth, where constellations seem fixed and eternal. But every star is a temporary structure, a balancing act between two opposing forces. On one side is gravity, pulling inward, trying to compress the star's enormous mass into the smallest possible spacing. On the other side is the energy generated by nuclear fusion at the star's core, pushing outward, resisting collapse. For most of a star's life, these two forces exist in a state of equilibrium. Gravity pulls, fusion pushes. The star holds its shape, radiating light and heat across space for millions or even billions of years. But fusion requires fuel. Deep in the core, hydrogen atoms are pressed together under extraordinary temperature and pressure, fusing into helium and releasing energy in the process. This is the reaction that powers our own sun, converting roughly 600 million tons of hydrogen into helium every second. It has been doing this for approximately 4.5 billion years, and it will continue for another 5 billion before its hydrogen begins to run low. The sun, however, is not massive enough to produce a black hole. Its fate will be quieter, a slow expansion into a red giant, followed by a gentle shedding of its outer layers, and a gradual cooling into a white dwarf. It will fade, but it will not collapse. For a star to produce a black hole, it must be far more massive. Current scientific understanding places the threshold at roughly 20 to 25 times the mass of the sun, though the exact boundary depends on the star's composition, its rate of rotation, and the details of its late-stage nuclear burning. These massive stars live fast. Their enormous gravitational pressure drives fusion at a furious rate, consuming hydrogen in their cores, not over billions of years, but over mere millions. A star 30 times the mass of the sun might exhaust its hydrogen in as little as 5 to 10 million years, a brief flash compared to the sun's 10 billion year lifespan. When the hydrogen runs out, the core contracts slightly under gravity, temperatures rise, and a new reaction begins. Helium atoms, the product of hydrogen fusion, begin fusing into carbon. This buys the star more time, but not much. Helium burning is less efficient and produces less energy per reaction. When the helium is consumed, the core contracts again, temperatures rise further, and carbon begins fusing into neon, then neon into oxygen, then oxygen into silicon. Each stage burns faster than the last. Each stage produces less energy. Each stage brings the star closer to a boundary it cannot cross. The final stage is silicon burning. Silicon fuses into iron, and iron is where the process stops. Unlike every element before it, iron cannot release energy through fusion. Fusing iron requires energy rather than producing it. When the core of a massive star becomes dominated by iron, the engine that has held the star together for millions of years simply switches off. There is no next reaction. There is no deeper fuel. Gravity, which has been patiently waiting since the moment the star was born, is suddenly unopposed. What happens next unfolds in less than a second. The iron core, no longer supported by outward pressure, collapses inward at speeds approaching a quarter of the speed of light. Temperatures soar past 10 billion degrees. Densities exceed anything found elsewhere in the observable universe. In this environment, the iron nuclei themselves are torn apart by the intense radiation, undoing in an instant the fusion work of millions of years. Electrons are forced into protons, creating neutrons and releasing a flood of ghostly particles called neutrinos. The collapsing core becomes an incomprehensibly dense ball of neutrons, a proto-neutron star, in a fraction of a second. If the original star was at the lower end of the mass range, this neutron core stabilizes. The strong nuclear force and neutron degeneracy pressure halt the collapse, and the result is a neutron star, an object roughly 20 kilometers across, but containing more mass than the Sun, spinning rapidly and radiating beams of energy into space. Neutron stars are among the densest objects in the known universe. A single teaspoon of neutron star material would weigh roughly 6 billion tons on Earth. But if the original star was massive enough, if the collapsing core exceeds approximately 2 to 3 solar masses, a boundary known as the Tolman-Oppenheimer-Volkoff limit, then not even the strong nuclear force can resist gravity. The neutron core continues to collapse. There is no known force in physics capable of stopping it. Matter compresses beyond the density of atomic nuclei, beyond any state that current science can describe with confidence, and the result is a black hole. The moment the collapsing matter crosses a critical density threshold, an event horizon forms. Space-time curves so steeply around the compressed mass that light itself cannot escape. From this moment forward, the interior of the collapsing region is permanently sealed off from the rest of the universe. Whatever happens inside, whatever state the matter reaches, whatever geometry space-time assumes, remains hidden behind the event horizon. Meanwhile, the outer layers of the star, still falling inward, strike the newly formed dense core and rebound outward in one of the most energetic events in nature, a core collapse supernova. The explosion releases more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. For a brief period, the dying star can outshine an entire galaxy. Heavy elements forged in the explosion, gold, platinum, uranium, and dozens of others, are scattered into space, eventually becoming part of new stars, new planets, and in at least one case, new life. The supernova is visible. The shockwave is detectable. The neutrino burst can be measured by instruments on Earth, but the black hole itself makes no announcement. It simply exists a region of space-time where gravity is won completely, surrounded by the expanding debris of the star that created it. Not every massive star produces a black hole through this dramatic sequence. Some stars may collapse so completely that no supernova occurs at all. These events, sometimes called failed supernovae, involve the entire star falling inward without the rebound explosion. The star simply vanishes from the sky, leaving behind a black hole and little else. Astronomers have identified a small number of candidates for such disappearances, massive stars that were observed and then, over a period of months or years, faded from view without producing the expected supernova. This process, the gravitational collapse of a massive star, produces what scientists call a stellar mass black hole. These objects typically contain between 5 and roughly 50 solar masses, though some may be larger. They are scattered throughout galaxies, often invisible, unless they happen to be near enough to another star to pull material from it. When a black hole draws matter from a companion star, that material spirals inward, forming a disk of superheated gas called an accretion disk. Friction within the disk heats the gas to millions of degrees, causing it to emit X-rays that can be detected by space-based telescopes. It was through these X-ray emissions that the first strong black hole candidate, Cygnus X1, located roughly 6,000 light-years from Earth, was identified in the early 1970s. Stellar mass black holes are, in a sense, the simplest black holes. Their formation is understood in broad terms. Their masses can be measured, their locations can sometimes be inferred. And yet, even for these relatively modest objects, the question remains, what is happening inside? The event horizon forms at the moment of collapse, sealing the interior from observation. The matter that created the black hole continues falling inward, but toward what? What structure, if any, exists at the center? What does space-time look like when compressed beyond every known limit? These questions do not depend on the size of the black hole. They apply equally to stellar mass black holes, born from collapsing stars, and to the supermassive black holes that sit at the centers of galaxies. The physics of the interior, the part hidden behind the event horizon, is the same mystery, regardless of scale. And it is toward that mystery that this documentary now turns. Before anything can be said about the interior of a black hole, something must first be understood about the boundary itself. The event horizon. Event horizon is not what most people imagine. It is not a wall. It is not a barrier made of energy or matter. It is not a glowing edge or a physical membrane stretched across space. If you were falling toward a black hole, you would not see the event horizon. You would not feel it. You would not hear it. You would cross it, and in the moment of crossing, nothing about your immediate surroundings would seem to change. This is one of the strangest predictions of general relativity. The event horizon is defined not by any local physical event, but by a global property of space-time. It is the surface beyond which no signal, no particle, no beam of light can ever reach the outside universe again. But for someone falling freely through it, there is no flash, no sensation, no boundary marker. Space-time at the event horizon is smooth. The curvature is finite. The forces for a sufficiently large black hole may even be gentle. The crossing happens in silence. And yet, from the perspective of someone watching from a safe distance, the story looks entirely different. This is where black holes begin to reveal how deeply they distort not only space but time. General relativity describes space-time as a single interwoven fabric. Mass curves this fabric, and the greater the concentration of mass, the steeper the curvature. Near a black hole, this curvature becomes so extreme that the flow of time itself is affected. Clocks tick more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This is not a metaphor. It is not an illusion. It is a measured, confirmed physical effect. On the surface of the Earth, gravitational time dilation is extraordinarily small. A clock at sea level runs very slightly slower than a clock on a mountaintop by a difference so tiny that it requires atomic clocks to detect roughly 1 second over every 30 million years. Near a neutron star, the effect becomes more pronounced. Near a black hole, it becomes dramatic. And at the event horizon itself, the effect reaches its mathematical extreme. Imagine a spacecraft falling toward a stellar mass black hole, one containing perhaps 10 times the mass of the Sun. Aboard the spacecraft is a clock, and far away, watching through a telescope, is a distant observer with a clock of their own. As the spacecraft descends deeper into the gravitational field, the distant observer notices something remarkable. The spacecraft's clock appears to slow down, not because anything is wrong with the clock, but because time itself, as measured from far away, flows more slowly near the black hole. The closer the spacecraft gets to the event horizon, the slower its clock appears to tick. At first, the difference is subtle. But as the spacecraft approaches the event horizon, the slowing becomes extreme. The distant observer watches the spacecraft appear to decelerate, its light shifting toward the red end of the spectrum, a phenomenon called gravitational redshift. The photons, climbing away from the black hole, lose energy as they fight against the gravitational pull, stretching to longer wavelengths, becoming dimmer and redder. The spacecraft seems to hang near the event horizon, moving more and more slowly, its image growing fainter and redder as though time aboard. It is grinding to a halt. From the distant observer's perspective, the spacecraft never actually crosses the event horizon. It approaches asymptotically, fading from view, its final image frozen and stretched into an ever dimmer ghost of light. This is not because the spacecraft has stopped. It is because the light, carrying information about its crossing, can no longer reach the outside universe. The event horizon is the point where outbound light is precisely balanced against the inward pull of gravity. And beyond it, the balance tips entirely inward. But aboard the spacecraft, the experience is profoundly different. The falling observer notices nothing unusual at the moment of crossing. Their clock continues to tick normally. Their instruments continue to function. The stars behind them may appear distorted by the extreme curvature of space-time light bending around the black hole in strange patterns, but the event horizon itself passes without ceremony. One moment they are outside, the next they are inside, and from that moment forward, every possible path through space-time leads deeper inward. This asymmetry between the falling observer and the distant watcher is one of the most important features of black hole physics. It is not a trick of perception. Both perspectives are equally valid descriptions of reality, viewed from different reference frames. General relativity does not privilege one over the other. The distant observer genuinely measures the spacecraft as never crossing. The falling observer genuinely experiences a smooth crossing. Both are correct within their own frames of reference. This is the kind of statement that sounds contradictory, but follows directly from the mathematics of curved space-time. The size of a black hole's event horizon depends on its mass. For a non-rotating black hole described by what physicists call the Schwarzschild solution, after the German physicist Karl Schwarzschild, who derived it from Einstein's equations in 1916, the radius of the event horizon is directly proportional to the mass. This radius is called the Schwarzschild radius. For a black hole with the mass of our Sun, the Schwarzschild radius would be approximately 3 kilometers. For a black hole with 10 solar masses, it would be roughly 30 kilometers. For the supermassive black hole at the center of the Milky Way, Sagittarius, a star with its 4 million solar masses, the Schwarzschild radius is approximately 12 million kilometers large, but still smaller than the orbit of Mercury around the Sun. This scaling has a profound consequence for anything approaching the event horizon. The experience of crossing depends enormously on the size of the black hole. Near a small stellar mass black hole, the curvature of space-time changes rapidly over short distances. This means that the gravitational pull on the near side of an extended object is significantly stronger than the pull on the far side. The result is a tidal force, a stretching along the direction of fall, and a compression perpendicular to it. For a human body, falling feet first toward a 10 solar mass black hole, the difference in gravitational acceleration between the feet and the head would become enormous before the event horizon is reached. The body would be stretched vertically and compressed horizontally, pulled apart like warm glass into a thin, elongated strand. Physicists, with a precision that borders on dark humor, call this process spaghettification. Spaghettification is not gentle. For a small black hole, the tidal forces become lethal millions of kilometers before the event horizon. the falling observer would be torn apart long before crossing the boundary. There remains a stream of superheated plasma, stretched into an impossibly thin thread, would spiral inward, contributing their matter and energy to the black hole's mass. But for a supermassive black hole, the situation is different. Because the event horizon is so much larger, the curvature of space-time at the horizon is actually gentler. The change in gravitational acceleration across a human-sized object at the event horizon of a billion-sun solar mass black hole would be negligible. A person falling into such a black hole would cross the event horizon intact, unharmed, unaware of the crossing. The tidal forces that would have destroyed them near a smaller black hole simply do not become significant until much deeper inside. This is a counterintuitive result. The most massive black holes in the universe, the ones containing billions of solar masses, sitting at the centers of the largest galaxies, are, in a certain sense, the gentlest to cross into. Their event horizons are enormous, their surface gravity is modest by black hole standards, and the tidal forces at the crossing point are small. It is only after crossing, as the observer falls deeper and deeper, that the curvature begins to steepen and the forces begin to grow. Carl Schwarzschild derived the first exact solution to Einstein's field equations describing such an object in December 1915, just weeks after Einstein published the final form of general relativity. And while Schwarzschild himself was serving on the Eastern Front of the First World War, he sent his solution to Einstein in a letter from the trenches. Einstein was reportedly surprised that an exact solution could be found so quickly. Schwarzschild died the following year at the age of 42, likely never knowing the full significance of what he had discovered. His solution described the simplest possible black hole, one with mass but no electric charge and no rotation. It would take decades before physicists fully understood the implications, and even longer before they accepted that such objects might actually exist in nature. For most of the 20th century, the event horizon was treated as a mathematical curiosity, an artifact of the equations, rather than a real physical boundary. Many physicists believed that some unknown mechanism would prevent matter from collapsing far enough to form one. It was not until the 1960s and 1970s, through the work of Roger Penrose, Stephen Hawking, John Wheeler, and others, that the theoretical case for black holes became overwhelming. Penrose's singularity theorems, published in 1965, demonstrated that once matter collapses past a critical point, the formation of a singularity, and therefore an event horizon, is essentially inevitable under general relativity. This work later earned Penrose a share of the 2020 Nobel Prize in Physics. The event horizon, then, is not a thing. It is a consequence, a boundary, that emerges from the geometry of space-time when mass is concentrated beyond a certain density. It cannot be touched, measured locally, or detected by any instrument passing through it. It exists only as a global feature of space-time, visible only in the mathematical structure of the solution, and yet its consequences are absolute. Once crossed, there is no return, no engine, no force, no technology can carry anything back outward. The event horizon is the universe's point of no return, enforced not by any wall or barrier, but by the shape of space-time itself. And so the question sharpens. If the crossing is smooth, if the falling observer notices nothing unusual, if their clock continues to tick and their instruments continue to function, then what happens next? What does the interior look like? What does physics predict for the journey from the event horizon to the center? The answers that general relativity provides are startling, beautiful, and ultimately incomplete, and they begin with a single, deeply unsettling idea. Beyond the event horizon, the roles of space and time reverse. This is perhaps the most disorienting prediction in all of general relativity, and it requires patience to absorb. Beyond the event horizon of a black hole, space and time exchange their roles, not metaphorically, not poetically, mathematically, structurally, in the very equations that describe the geometry of space-time. The coordinate that once described radial distance, the direction pointing inward or outward, takes on the properties of time, the poppy, and the coordinate that once described time takes on the properties of space. What this means in physical terms is profound. Outside the event horizon, time moves forward and space offers freedom. A traveler can choose to move left or right, up or down, closer to the black hole or farther away. The future is ahead and spatial directions are open. But inside the event horizon, that freedom inverts. The radial direction, the line from the event horizon toward the center, is no longer a direction in space. It has become a direction in time. Moving inward is no longer a choice. It is the future. Just as no object in the external universe can travel backward in time, no object inside the event horizon can move outward in space. The center of the black hole is not a place ahead. It is a moment ahead. It is the future, and it cannot be avoided. This is not a force pulling the falling observer inward. It is not a wind, a current, or a gravitational tug in the ordinary sense. It is the shape of space-time itself, curved so completely that every possible trajectory, every world line, every path through space and time leads to smaller and smaller radial values. No matter which direction the observer points their engines, no matter how much thrust they apply, no matter how cleverly they try to navigate, their future contains only one destination, the center. The analogy that physicists sometimes offer is this: outside the black hole, asking someone to avoid the center is like asking them to avoid a particular city. They can steer around it. Inside the black hole, asking them to avoid the center is like asking them to avoid next Tuesday. They cannot. It will arrive regardless of what they do. The singularity is not a place to be dodged. It is a moment to be reached. This reversal is embedded in the mathematics of the Schwarzschild solution. In the standard form of the metric, the mathematical object that describes the geometry of space-time, there is a term involving the radial coordinate and a term involving the time coordinate. Outside the event horizon, the radial term carries a positive sign associated with spatial distance, and the time term carries a negative sign associated with the flow of time. At the event horizon, these signs change. The term that was spatial becomes temporal, and the term that was temporal becomes spatial. The mathematics does not distinguish between space and time by any fundamental marker. It distinguishes them by sign, by the direction of causality, by whether movement along that coordinate is optional or inevitable. And at the event horizon, that distinction flips. For the falling observer, this reversal does not arrive as a sudden transformation. There is no moment of reorganization, no flash of reorientation. Space-time transitions smoothly. The observer crosses the event horizon and continues falling, and the mathematics describes their trajectory as a smooth curve through a smoothly changing geometry. The reversal is a global feature of the solution, visible in the equations, but not experienced as a local event. What the observer does experience, however, depends on the size of the black hole and how far they have fallen. For a stellar mass black hole, the tidal forces would have already torn the observer apart before reaching the event horizon, as described earlier. But for the purpose of understanding what general relativity predicts about the interior, it is useful to consider an idealized observer, one falling freely into a supermassive black hole, where the event horizon crossing is gentle and the tidal forces remain manageable for some distance inside. Sumo. Such an observer, having crossed the event horizon of a supermassive black hole, would initially notice remarkably little change. Their instruments would continue functioning. Light from stars behind them, already distorted by the extreme curvature outside, would continue to reach them. though increasingly blue-shifted and concentrated into a shrinking bright ring above. Light from the universe outside, photons that crossed the event alongside or after the observer, would still be visible. The observer would not be plunged into absolute darkness. They would not immediately perceive the walls closing in. The crossing is smooth, and the first moments inside might feel, from a local perspective, almost ordinary. But as the observer continues to fall and fall, they must, because the center is now the future. The curvature of space-time begins to increase. The tidal forces grow. The difference in gravitational acceleration between the observer's head and feet, negligible at the event horizon of a supermassive black hole, begins to steepen. Space itself, in the direction perpendicular to the fall, begins to contract. The observer is being stretched along the direction of fall and compressed from the sides, slowly at first, then with increasing intensity. General relativity describes this process with mathematical precision. The Riemann curvature tensor, which encodes the tidal forces at every point in spacetime, which grows without bound as the radial coordinate decreases. The forces are gentle near the event horizon of a large black hole, but they increase as the observer falls deeper. At some point, the exact distance depending on the black hole's mass, the tidal forces become strong enough to overwhelm any material structure. Metal stretches, rock fractures, atoms are distorted. Eventually, even subatomic particles are subjected to forces that current physics cannot fully describe. The geometry of the interior is not what everyday intuition might suggest. The observer is not falling down a tunnel. There are no walls. There is no floor approaching from below. The interior of a black hole, as described by general relativity, is a region of space-time with a specific geometric structure, a structure that curves inward from every direction, funneling all trajectories toward the singularity. If the observer looks around, they see not a confined space, but a distorted universe, light, bent and compressed, images from the outside world, warped into strange patterns, the sky shrinking into an increasingly concentrated disk of blue-shifted radiation above them. This visual experience, though impossible to observe directly, has been modeled extensively using computer simulations based on general relativity. Researchers have traced the paths of light rays through the curved spacetime of a black hole interior, producing visualizations that reveal what a camera, falling freely past the event horizon, would theoretically record. These simulations show that the observer's view of the outside universe becomes compressed into a bright ring that slowly narrows as the fall continues. Meanwhile, looking downward toward the singularity reveals only darkness. Not the darkness of empty space, but the darkness of a region from which no light has ever escaped, and where the geometry of space-time prevents any light from forming coherent images. The duration of the fall from the event horizon to the singularity depends on the mass of the black hole. For a stellar mass black hole of 10 solar masses, the free fall time from the event horizon to the singularity is extraordinarily brief, on the order of a few tens of microseconds. The observer, if not already destroyed by tidal forces outside the horizon, would reach the singularity almost instantly. For the supermassive black hole at the center of the Milky Way, with its 4 million solar masses, the free fall time extends to roughly 20 seconds. For the most massive black holes known, those containing 10 billion solar masses or more, found at the centers of the largest galaxies, the free fall time could stretch to many hours. This means that, in principle, an observer crossing the event horizon of a sufficiently massive black hole could survive for hours inside, watching the distorted universe above, feeling the tidal forces gradually grow, knowing with absolute certainty that no escape is possible. This is not a comforting thought, but it is what the equations predict. General relativity, stripped of drama and metaphor, describes the interior of a black hole as a finite amount of time between two boundaries, the event horizon, which is crossed smoothly, and the singularity, which is reached inevitably. The concept of the singularity requires careful language. In the mathematical framework of general relativity, the singularity is the point at which certain quantities' curvature, density, tidal forces become infinite. It is not a point in space, despite how it is often depicted. It is better understood as a moment in time, the final moment, the future endpoint of every trajectory inside the event horizon. When the mathematics says the curvature becomes infinite, it is saying that the equations of general relativity can no longer produce meaningful answers. The theory breaks down. The description fails. This breakdown is not a subtle technical detail. It is one of the most significant unsolved problems in theoretical physics. General relativity, the theory that describes gravity as the curvature of space-time, has been tested with extraordinary precision in every environment, where it can be measured, from the motion of planets to the bending of light around galaxies to the detection of gravitational waves from colliding black holes. It has never failed an observational test, and yet it predicts its own failure at the center of every black hole. The singularity is not a prediction of infinite density. It is a prediction that the theory itself is incomplete. Most physicists believe that the singularity, as described by general relativity, does not physically exist. Instead, they expect that at some point near where the singularity would form, the effects of quantum mechanics, the physics of the very small, become important enough to modify the picture. In this view, the singularity is a signal that a new theory is needed, one that combines the curvature of space-time, described by general relativity, with the probabilistic, discrete nature of reality, described by quantum mechanics. This hypothetical theory is commonly called quantum gravity, and despite decades of effort, no complete experimentally verified theory of quantum gravity yet exists. What actually happens at the center of a black hole? What replaces the singularity in a complete theory remains unknown. Several theoretical proposals exist, and they will be explored later in this documentary. But for now, the essential point is this. General relativity gives a remarkably clear description of the journey from the event horizon inward. It describes the reversal of space and time, the growing tidal forces, the compression of the visible universe, and the finite duration of the fall. It describes everything up to the singularity with mathematical elegance. And then, at the singularity itself, the description ends. The theory does not crash loudly. It does not produce an error message. It simply yields infinity's quantities that have no physical meaning and falls silent. What lies beyond that silence is one of the great questions of 21st century physics. But before turning to the efforts to answer that question, there is another layer of complexity to consider. The Schwarzschild solution, the one described so far, applies to a black hole that does not rotate. It describes the simplest possible geometry mass, without spin, without charge, without any additional structure. It is elegant, exact, and deeply informative. But most real black holes in the universe are not described by the Schwarzschild solution. Most black holes rotate, and rotation changes everything about the interior. It introduces new structures, new possibilities, and new mysteries that push the limits of general relativity even further. In 1963, a New Zealand mathematician named Roy Kerr found something that had eluded physicists for nearly half a century. Working at the University of Texas at Austin, Kerr discovered an exact solution to Einstein's field equations describing a black hole that rotates. The solution was elegant, compact, and profoundly important because virtually every black hole in the universe rotates. Stars rotate. When they collapse, that rotation is preserved and amplified just as a figure skater spins faster by pulling their arms inward. The Schwarzschild solution, beautiful as it is, describes an idealized object that does not exist in nature. The Kerr solution describes the real thing. And the interior of a rotating black hole is far stranger than anything the Schwarzschild geometry predicts. The first difference is immediately apparent in the structure of the boundary. A non-rotating black hole has a single event horizon, one smooth spherical surface marking the point of no return. A rotating black hole has two. The outer event horizon functions much like the Schwarzschild event horizon. It is the boundary beyond which escape becomes impossible. Light and matter that cross it are committed to the interior, but inside the outer horizon, the geometry of space-time changes in ways that have no analogue in the non-rotating case. The falling observer, having crossed the outer boundary, does not immediately encounter a singularity. Instead, they enter a region between the outer and inner horizons, a region where the radial coordinate has once again taken on the character of time, where falling inward is inevitable, but where the singularity is not yet the immediate future. At the inner horizon, something remarkable happens. The roles of space and time, which reversed at the outer horizon, reverse again. The radial direction becomes spatial once more. Movement inward is no longer compelled by the geometry of space-time. The observer, having passed through two horizons, finds themselves in a region where, according to the mathematics, they can once again choose their direction. They can move inward, outward, or sideways. The crushing inevitability that defined the Schwarzschild interior is, in the Kerr geometry, temporarily lifted. This is already a dramatic departure from the non-rotating case. But the differences do not end there. At the center of a Schwarzschild black hole, the singularity is a point, a zero-dimensional location where curvature becomes infinite and the equations break down. In a Kerr black hole, the singularity is not a point, it is a ring, a one-dimensional loop of infinite curvature, lying in the equatorial plane of the black hole's rotation. The ring singularity has a finite radius, determined by the angular momentum of the black hole, and it introduces geometric possibilities that border on the surreal. In the Schwarzschild interior, every trajectory leads to the singularity. There is no way around it. It is the future, and the future cannot be avoided. But in the Kerr interior, the ring singularity can, in principle, be avoided. An observer falling along the axis of rotation, approaching the ring from above or below, could pass through the center of the ring without ever touching the singularity itself. The ring has an interior, and that interior, according to the equations, opens into a new region of space-time. What lies on the other side of the ring singularity is one of the most debated predictions in all of theoretical physics. The Kerr solution, taken at face value, suggests that passing through the ring leads to a different region of space-time, not the universe the observer came from, but something else entirely. Some interpretations describe this region as a mirror universe with reversed gravitational properties, where gravity repels rather than attracts. Others describe it as a gateway to a separate space-time altogether. The mathematics permits these interpretations. Whether nature does is another question entirely. Most physicists regard the deep interior of the Kerr solution with considerable caution. The inner horizon, including the ring singularity and whatever lies beyond it, is mathematically valid but physically suspect. The reason lies in a phenomenon known as mass inflation instability. When Kerr published his solution, it described an eternal, perfectly symmetric, rotating black hole, one that had existed forever and would continue to exist forever, undisturbed by any external influence. Real black holes are not like this. They form from collapsing matter. They absorb radiation. They are embedded in a universe filled with light, particles, and gravitational waves. And when even a tiny amount of external radiation crosses the outer horizon and falls toward the inner horizon, something violent happens. The inner horizon acts as a lens, focusing incoming radiation to extreme intensities. A photon that crosses the outer horizon at modest energy is blue-shifted, compressed to shorter wavelengths and higher energies as it approaches the inner horizon. In the idealized Kerr geometry, this blue shift becomes infinite at the inner horizon itself. The energy density of incoming radiation grows without bound. In physical terms, this means that the inner horizon of a real rotating black hole is likely unstable. Any perturbation, no matter how small, is amplified to catastrophic levels. The smooth, well-behaved geometry that Kerr's equations predict for the region between the inner horizon and the ring singularity may not survive in the presence of even the faintest whisper of infalling radiation. This instability, first studied in detail by physicists Eric Poisson and Werner Israel in 1990, suggests that the interior of a real rotating black hole may be very different from the interior of the idealized Kerr solution. The inner horizon may be replaced by a region of extreme curvature, a kind of singularity in its own right, though different in character from the point or ring. Singularities of the classical solutions, the precise nature of this region remains an active area of research. What this means for the falling observer is sobering. The tantalizing features of the Kerr interior, the avoidable ring singularity, the passage to another space-time, the restoration of spatial freedom beyond the inner horizon, may exist only in the mathematical idealization. In a real black hole, formed from real matter and bathed in real radiation, these features may be destroyed by the very instabilities that the idealization ignores. But the Kerr solution introduces another feature that is not confined to the deep interior, one that has direct measurable consequences in the space outside the event horizon. This feature is called the ergosphere. The ergosphere is a region surrounding a rotating black hole, extending beyond the outer event horizon, where space-time itself is dragged along by the rotation of the black hole. This effect, known as frame dragging, or the Lense-Thirring effect, is a prediction of general relativity that applies near any rotating mass. The Earth produces frame dragging, though the effect is extraordinarily small. Near a rotating black hole, frame dragging becomes extreme. Within the ergosphere, space-time is dragged so forcefully that no object, no matter how powerful its engines, can remain stationary. Everything within the ergosphere must rotate in the direction of the black hole's spin. Standing still becomes physically impossible, not because of a force pushing the object, but because the space-time in which the object exists is itself rotating. The ergosphere is not behind the event horizon, it lies outside it. An object can enter the ergosphere and, with sufficient energy, escape again. It can return to the outside universe. This makes the ergosphere fundamentally different from the event horizon. It is a region of extreme space-time distortion, but not a region of no return. In 1969, the British physicist Roger Penrose proposed a remarkable thought experiment exploiting this distinction. He showed that it is theoretically possible to extract energy from a rotating black hole by sending an object into the ergosphere, splitting it in two, and allowing one piece to fall across the event horizon while the other escapes. The escaping piece can carry more energy than the original object brought in, with the excess coming from the rotational energy of the black hole itself. The black hole slows down slightly, losing angular momentum, while the escaping fragment carries away the extracted energy. This process, known as the Penrose process, demonstrates that rotating black holes are not merely passive gravitational traps. They are, in a certain sense, engines capable of releasing energy through the geometry of their rotating space-time. A related mechanism applicable to electromagnetic fields near rotating black holes was proposed by Roger Blandford and Roman Znajek in 1977. The Blandford-Znajek process describes how magnetic field lines threading through a rotating black hole's ergosphere can extract rotational energy and channel it into powerful jets of plasma. These jets have been observed in nature, enormous beams of matter and radiation, shooting outward from the centers of active galaxies at velocities approaching the speed of light. The energy source powering these jets in many cases appears to be the rotational energy of a supermassive black hole, extracted through a mechanism closely related to what Blandford and Znajek described. The existence of the ergosphere and the processes it enables have been confirmed, at least in broad terms, by astronomical observations. The relativistic jets emerging from active galactic nuclei carry enormous amounts of energy, sometimes exceeding the total luminous output of the host galaxy. The only known mechanism capable of producing such energy involves the rotational energy of a supermassive black hole, mediated by the extreme space-time geometry of the ergosphere. Frame dragging itself has been directly measured near the Earth, though at an incomparably smaller scale. The Gravity Probe B mission, launched by NASA in 2004 and reporting results in 2011, used 4 ultra-precise gyroscopes in Earth orbit to measure the frame-dragging effect produced by the Earth's rotation. The measured precession, roughly 37 milliarc-seconds per year, a value so small it required years of careful data analysis to extract, agreed with the predictions of general relativity. While the effect near Earth is minuscule, it confirms the reality of the underlying phenomenon. Near a rapidly rotating black hole, the same effect becomes dominant, reshaping the entire geometry of space-time. The Kerr solution, then, paints a far richer picture of black hole interiors than the Schwarzschild solution alone. It introduces multiple horizons, a ring-shaped singularity, the possibility of avoiding the singularity, the theoretical existence of passages to other space-time regions, and the measurable reality of frame dragging and energy extraction. But it also introduces deep questions about the stability and physical reality of its most exotic predictions. The idealized Kerr interior may not survive contact with the real universe. The features that make it most fascinating, the inner horizon, the ring, the passage beyond, may be artifacts of mathematical perfection that nature, in its messy radiation-filled reality, does not preserve. This tension between mathematical elegance and physical reality runs through all of black hole physics. The equations offer clean, beautiful answers. Nature, when examined more closely, reveals complications that the equations did not anticipate. And nowhere is this tension more acute than in the question that has driven some of the most intense debates in modern physics, a question that begins not with general relativity, but with quantum mechanics, and that concerns not the geometry of space-time, but something far more fundamental. It is the question of what happens to information. In 1974, Stephen Hawking published a paper that quietly transformed the study of black holes from a problem of geometry into a crisis of fundamental physics. The paper was titled Black Hole Explosions, and its central result was so unexpected, so deeply unsettling to the foundations of physics, that its consequences are still being debated more than 50 years later. Hawking had been studying what happens when the principles of quantum mechanics are applied to the region near a black hole's event horizon. General relativity describes the event horizon as a smooth boundary in curved space-time. Quantum mechanics describes the vacuum of space as anything but empty, a seething, turbulent landscape of virtual particle pairs constantly flickering into and out of existence. These virtual pairs, consisting of a particle and its antiparticle, normally appear together and annihilate each other almost instantly, borrowing energy from the vacuum for the briefest of moments before returning it. In flat, undistorted space-time, this process leaves no lasting trace, but near the event horizon of a black hole, the curvature of space-time changes the rules. Hawking showed that when a virtual pair forms near the horizon, it is possible for one particle to fall inward across the boundary, while the other escapes outward into space. The escaping particle carries real energy away from the black hole. The infalling particle, from the perspective of an external observer, carries negative energy inward, reducing the black hole's total mass. The net effect is that the black hole emits radiation, a faint, steady glow of particles streaming away from the event horizon, drawn from the quantum vacuum by the curvature of space-time. This radiation is now called Hawking radiation. Its spectrum, the distribution of energies among the emitted particles, matches that of a thermal body, an object radiating heat. The temperature of this radiation is inversely proportional to the mass of the black hole. A stellar mass black hole containing 10 times the mass of the Sun would have a Hawking temperature of roughly 6 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe at approximately 2.7 Kelvin. Such a black hole would absorb far more energy from its surroundings than it radiates, and would therefore grow rather than shrink. Hawking radiation from stellar mass or supermassive black holes is, for all practical purposes, undetectable with any current or foreseeable technology. But for very small black holes, hypothetical objects, far less massive than any star, the temperature would be much higher and the radiation much more intense. As a black hole radiates, it loses mass. As it loses mass, its temperature rises. As its temperature rises, it radiates faster. The process accelerates. In the final moments of a sufficiently small black hole's existence, the radiation becomes explosive, a burst of particles and energy. As the last of the mass is converted into radiation, the black hole evaporates entirely, leaving behind only a fading flash of Hawking radiation. This prediction that black holes are not permanent, that they slowly radiate their mass away and eventually vanish, was remarkable enough on its own. It connected general relativity and thermodynamics in a single physical process. It gave black holes a temperature, an entropy, and a finite lifespan. It transformed them from eternal prisons into temporary objects with a beginning, a middle, and an end. But the truly disturbing implication lay not in the radiation itself, but in what the radiation contained, or rather, what it did not contain. Hawking's calculation showed that the radiation emitted by a black hole is thermal. It carries a temperature and a spectrum, but it carries no detailed information about what fell into the black hole. A black hole formed from the collapse of a star made of hydrogen would emit exactly the same Hawking radiation as a black hole of identical mass formed from the collapse of a star made of iron. A black hole that swallowed a library would radiate the same spectrum as one that swallowed an equal mass of empty space. The radiation depends only on the black hole's mass, charge, and angular momentum, the three quantities that define a black hole's external properties. Everything else, every detail about the matter that formed the black hole, every book, every atom, every quantum state appears to be erased. This is the black hole information paradox, and it strikes at one of the deepest principles in all of physics. In quantum mechanics, information is never destroyed. This is not a guideline or a practical observation. It is a mathematical property of the theory itself. The equations of quantum mechanics are unitary. They preserve the total amount of information in a closed system. A quantum state at one moment can always, in principle, be traced backward or forward to determine the state at any other moment. The information may become scrambled, rearranged, or spread across an enormous number of particles, but it is never lost. This principle, the unitarity of quantum mechanics, is one of the cornerstones of modern physics. If Hawking's calculation is correct, black hole evaporation violates this principle. The information that fell into the black hole is not encoded in the outgoing radiation. When the black hole finally evaporates completely, that information has simply vanished from the universe. It entered the black hole. The black hole radiated thermally. The radiation carried no record of what went in. And when the black hole is gone, the information is gone with it. Hawking initially accepted this conclusion. He argued that black holes genuinely destroy information, and that quantum mechanics, as applied to gravity, must be modified to accommodate this destruction. This was a radical position. It meant that the laws of physics, at their deepest level, were not reversible. It meant that the universe could permanently forget. Many physicists disagreed, sometimes intensely. The idea that information could be destroyed contradicted not only quantum mechanics, but also the logical structure of physical prediction. If information is lost, the future cannot be fully determined from the past, and the past cannot be fully reconstructed from the future. The deterministic framework that underpins all of physics, classical and quantum, would be fundamentally broken. The disagreement between Hawking and his opponents crystallized into one of the most famous scientific wagers in modern physics. In 1997, Hawking and Kip Thorne bet against John Preskill that information falling into a black hole is permanently lost. Preskill maintained that information must somehow escape, preserving the unitarity of quantum mechanics. The bet remained unresolved for years, a symbol of the deep uncertainty at the intersection of gravity and quantum theory. In 2004, Hawking publicly conceded the bet. He announced at a physics conference that he had reconsidered his position and now believed that information is preserved, that it somehow escapes the black hole, encoded in subtle correlations within the Hawking radiation. The concession made headlines, but it resolved less than it appeared to. Hawking did not provide a complete mechanism for how information escapes. He offered a proposal based on a particular mathematical approach to quantum gravity, but the details were contested, and many physicists remained unconvinced that the problem had been solved. Thorne, notably, did not concede. He maintained that the question remained open. The information paradox has generated an extraordinary number of theoretical proposals over the decades. Each attempts to resolve the conflict between Hawking's calculation and the unitarity of quantum mechanics, and each carries its own implications for what happens inside a black hole. One class of proposals suggests that information never actually enters the black hole. In this view, information about infalling matter is somehow encoded on the event horizon itself, stored on the two-dimensional boundary rather than in the three-dimensional interior. This idea connects to a broader theoretical framework known as the holographic principle, which proposes that all the information contained within any region of space can be described by a theory defined on the boundary of that region. The holographic principle, developed in the 1990s by Gerard 't Hooft and Leonard Susskind, suggests that the three-dimensional interior of a black hole may be, in some deep sense, equivalent to a two-dimensional description living on the event horizon. If this is correct, then the information paradox dissolves. Information is never lost because it was never truly inside the black hole. It was always on the surface, encoded in a form that is eventually released through Hawking radiation. The holographic principle has found strong mathematical support in a specific theoretical context known as the AD-SCFT correspondence proposed by Juan Maldacena in 1997. This correspondence establishes an exact mathematical equivalence between a gravitational theory in a particular type of curved spacetime and a non-gravitational quantum theory defined on the boundary of that spacetime. Within this framework, information is provably preserved. Black holes form, evolve, and evaporate, and the information that entered them is recovered in the outgoing radiation, encoded in increasingly complex correlations that become apparent only after extremely long times. The AD-SCFT correspondence is widely regarded as one of the most important theoretical discoveries of the past 3 decades, but it applies, strictly speaking, to a type of space-time geometry that differs from the geometry of our universe. Whether its lessons translate directly to real black holes in real space-time remains an open question. Another influential proposal, introduced by Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully in 2012, created a new puzzle rather than resolving the old one. Their analysis, known as the firewall argument, showed that 3 seemingly reasonable assumptions: the preservation of information, the validity of general relativity at the event horizon, and the standard rules of quantum field theory cannot all be true simultaneously. At least one must break down. If information is preserved through subtle correlations in Hawking radiation, as the holographic approach suggests, then the smooth, uneventful event horizon described by general relativity may not exist. Instead, an infalling observer might encounter a wall of high-energy radiation, a firewall at the event horizon, destroying anything that crosses it. The firewall proposal was deeply controversial. It contradicted the central prediction of general relativity, that the event horizon is locally smooth, and that a freely falling observer notices nothing unusual when crossing it. If firewalls exist, the gentle crossing described in earlier chapters of this documentary would be wrong. The event horizon would not be a quiet boundary. It would be a violent end. The debate over firewalls consumed the theoretical physics community for years. Some physicists accepted the argument and explored its consequences. Others proposed modifications to quantum mechanics or to the structure of space-time that would avoid the firewall while preserving information. Still others argued that the paradox itself might indicate a deeper misunderstanding, that the concepts of interior, exterior, and event horizon may need to be reformulated in a theory that fully unifies gravity and quantum mechanics. No consensus has been reached. The information paradox, more than 50 years after Hawking's original paper, remains one of the most important unsolved problems in theoretical physics. It is not merely a puzzle about black holes. It is a puzzle about the nature of information itself, about whether the universe keeps a perfect record of everything that has ever happened, or whether there are processes that permanently erase that record. The resolution, when it comes, will almost certainly require a deeper understanding of quantum gravity, a theory that does not yet exist in complete form. And whatever that resolution reveals about the fate of information will, inevitably, reveal something about what truly happens inside a black hole behind the event horizon, in the hidden region where the known laws of physics reach their limits. For most of the 20th century, black holes existed only in equations. They were predictions, consequences of a mathematical theory that had been tested in weaker gravitational fields but never confirmed in the extreme regime where event horizons form and space-time curves beyond recognition. Many physicists accepted that black holes were theoretically possible. Fewer were confident that nature actually produced them, and none could point to a single direct observation and say with certainty that a black hole had been seen. This was not for lack of trying. The problem was fundamental. A black hole, by definition, does not emit light. It does not shine. It does not reflect. It does not announce itself through any electromagnetic signal. Originating from within the event horizon, detecting a black hole meant detecting not the object itself, but its influence, the gravitational pull on nearby matter, the bending of light passing near it, the X-ray glow of superheated gas spiraling into it. These indirect signatures were suggestive, sometimes compelling, but never conclusive in the way that a direct image would be. The first strong observational candidate emerged in the early 1970s. Cygnus X1, a powerful X-ray source in the constellation Cygnus, was identified as a binary system, a visible supergiant star locked in orbit with an unseen companion. By measuring the orbital motion of the visible star, astronomers could calculate the mass of the invisible partner. The result was striking. The unseen object contained roughly 15 solar masses, far too heavy to be a white dwarf or neutron star. No known physics could produce a compact object of that mass without forming an event horizon. Cygnus X1 became the first widely accepted black hole candidate. Over the following decades, additional candidates accumulated. X-ray binary systems in the Milky Way revealed compact objects too massive for neutron star explanations. The centers of distant galaxies showed evidence of enormous concentrations of mass. Millions or billions of solar masses compressed into regions smaller than the solar system. Stars near the center of our own galaxy were observed orbiting an invisible point with extraordinary speed. Their trajectories consistent with a compact object of roughly 4 million solar masses. This object, Sagittarius A star, became the leading candidate for a supermassive black hole at the heart of the Milky Way. The evidence was strong, but still circumstantial. Mass estimates, orbital dynamics, and X-ray emissions pointed toward black holes, but they did not image one. They did not reveal the event horizon. They did not show the shadow that a black hole's gravity should cast against the glowing material around it. That changed on April 10, 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole. The image showed the supermassive black hole at the center of Messier 87, a giant elliptical galaxy in the Virgo cluster, approximately 55 million light-years from Earth. The black hole, designated M87 star, contains roughly 5 billion solar masses, more than 1,000 times the mass of Sagittarius A star. Its event horizon spans a region larger than the entire solar system, and in the image, it appeared exactly as general relativity predicted. A dark circular shadow, roughly the size of the event horizon, surrounded by a bright asymmetric ring of superheated gas. The image was not taken by a single telescope. No single telescope on Earth has the resolution necessary to resolve an object as small as a black hole's shadow at a distance of 55 million light-years. The angular size of M87 star's shadow, as seen from Earth, is approximately 40 microarcseconds, equivalent to reading a newspaper on the surface of the Moon. To achieve this resolution, the Event Horizon Telescope linked radio telescopes across the globe from Hawaii to Chile, from Spain to the South Pole, using a technique called very long baseline interferometry. By combining data from telescopes separated by thousands of kilometers, the collaboration effectively created a virtual telescope the size of the Earth. The data collection itself took place over several nights in April 2017. The resulting dataset was so large, roughly 5 petabytes, that it could not be transmitted electronically. Physical hard drives were shipped from each observatory to central processing facilities, where teams of scientists spent nearly 2 years calibrating, cross-checking, and reconstructing the image using multiple independent algorithms. The fact that all algorithms produced consistent results, the same ring, the same shadow, the same asymmetry, provided powerful evidence that the image reflected genuine structure rather than processing artifacts. The bright ring in the image corresponds to synchrotron radiation light emitted by electrons, spiraling at nearly the speed of light through magnetic fields in the superheated accretion flow surrounding the black hole. The asymmetry of the ring brighter on one side than the other is a consequence of relativistic beaming. Gas moving toward the observer appears brighter due to Doppler effects, while gas moving away appears dimmer. This asymmetry was predicted by general relativistic simulations long before the image was captured. The dark shadow at the center is not the event horizon itself. It is the black hole's shadow, the region from which photons are captured by the black hole's gravity and cannot reach the observer. The boundary of this shadow is determined by the photon's sphere, a region just outside the event horizon where photons can orbit the black hole on unstable circular paths. Photons passing just inside the photon sphere spiral inward and are captured. Photons passing just outside escape and can reach a distant telescope. The edge of the shadow corresponds to this critical boundary, and its size and shape are predicted by general relativity with remarkable precision. The M87 star image confirmed several key predictions. The shadow was circular to within measurement uncertainty, consistent with the Kerr solution for a rotating black hole. Its diameter matched the prediction for a black hole of 6.5 billion solar masses. The surrounding emission was consistent with simulations of magnetized accretion flows. In the Kerr spacetime, the image did not reveal the interior of the black hole. No observation can. But it confirmed that the exterior geometry behaves exactly as Einstein's equations predict. 3 years later, in May 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the supermassive black hole at the center of the Milky Way. This image was more technically challenging than M87 star, despite Sagittarius A star being much closer, because Sagittarius A star is roughly 1,000 times less massive than M87 star. The gas orbiting it moves much faster, and the emission pattern changes on timescales of minutes rather than days. Capturing a stable image required new computational techniques to account for this rapid variability. The resulting image showed the same fundamental features: a dark central shadow surrounded by a bright ring of emission. Once again, the size and shape of the shadow matched the predictions of general relativity for a black hole of approximately 4 million solar masses. The consistency between two independent observations, two different black holes, two different mass scales, two different galactic environments, both producing shadows that match the same theoretical framework, provided powerful confirmation that general relativity accurately describes the space-time geometry near event horizons. These images were triumphs of observation, engineering, and theoretical prediction, but they showed only the exterior. The shadow, the ring, the asymmetry, all of these features originate from the region outside the event horizon. The interior remains hidden. A different kind of observation, however, has provided information about black holes that even images cannot, not by capturing light, but by detecting the ripples that black holes create in the fabric of spacetime itself. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. The signal, designated GW15911, originated from the merger of two stellar mass black holes, approximately 1.3 billion light-years from Earth. One black hole contained roughly 36 solar masses, the other contained roughly 29. In the final fraction of a second before merger, the two black holes spiraled around each other at nearly the speed of light, releasing more energy in gravitational waves than the combined light output of all the stars in the observable universe during that same instant. The merged remnant was a single black hole of approximately 62 solar masses, 3 solar masses less than the combined mass of the two originals. That missing mass had been converted entirely into gravitational wave energy, radiated outward as ripples in space-time. LIGO detected these ripples as an extraordinarily tiny change in the length of its 4-kilometer-long detector arms, a change smaller than 1/10,000th the diameter of a proton. The signal matched the predictions of general relativity with extraordinary precision. The waveform, the shape of the gravitational wave signal over time, encoded the masses, spins, and orbital dynamics of the merging black holes. It also encoded the moment of merger, when the two event horizons touched and combined into one, and the subsequent ring-down, during which the newly formed black hole settled into a stable Kerr configuration, by radiating away its remaining asymmetries as gravitational waves. The ring-down phase is particularly significant for understanding black hole interiors. The frequencies and damping times of the ring-down oscillations, called quasi-normal modes, are determined entirely by the mass and spin of the final black hole. They are, in a sense, the black hole's natural vibrations, analogous to the tones produced by a struck bell. General relativity predicts these frequencies precisely, and the observed ring-down of GW1 Phi 091 Phi matched those predictions. This provides strong evidence that the final object is indeed a Kerr black hole, an object described entirely by its mass and spin, with no additional structure visible from the outside. Since that first detection, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave events from merging black holes, merging neutron stars, and mixed neutron star black hole mergers. Each detection has confirmed the predictions of general relativity in increasingly precise detail. The masses of the detected black holes have ranged from a few solar masses to over 100, revealing a population of stellar mass black holes that is larger and more diverse than many astronomers had expected. Gravitational wave observations have also raised new questions. Several detected black holes fall within a mass range roughly 50 to 130 solar masses that standard stellar evolution models struggle to explain. Stars massive enough to produce such heavy remnants are expected, under certain conditions, to explode so completely that no black hole remains. The existence of black holes in this mass gap suggests that some may have formed through previous mergers, through processes in dense stellar environments like globular clusters, or through pathways not yet fully understood. These observations, the Event Horizon Telescope images, and the LIGO gravitational wave detections have transformed black holes from theoretical constructs into observed physical objects. Their exterior properties are now measured, imaged, and confirmed with extraordinary precision. The geometry of space-time near the event horizon behaves exactly as general relativity predicts. The masses, spins, and merger dynamics follow the equations with remarkable fidelity, but the interior remains beyond reach. No image can penetrate the event horizon. No gravitational wave carries information from inside. The event horizon is, by construction, the boundary beyond which no signal escapes. Everything observed so far, every image, every waveform, every orbital measurement describes the exterior. The question of what happens inside, what structure exists at the center, what replaces the singularity in a complete theory, remains unanswered by observation. And yet, the precision of these observations has sharpened the theoretical questions. If general relativity describes the exterior so accurately, how far inward does its description hold? Does it remain valid all the way to the singularity? Or does it break down at some intermediate point? Is the smooth event horizon predicted by general relativity truly smooth? Or does quantum mechanics introduce structure, a firewall, a fuzzball, a membrane that modifies the crossing? The observations do not answer these questions directly, but they constrain the theoretical landscape, ruling out alternatives that deviate from general relativity's predictions in the observable regime. The gap between what has been observed and what remains hidden is both frustrating and inspiring. It is the gap in which the deepest questions of physics currently reside, questions about the nature of space-time, the fate of information, and the ultimate structure of reality at scales where both gravity and quantum mechanics matter. These questions cannot be answered by larger or more sensitive detectors alone. They require a deeper theory, one that unifies the two great frameworks of 20th century physics into a single, coherent description of nature. That search for a deeper theory is where this documentary now turns. Yet, the problem is not that physicists lack ideas about what happens inside a black hole. The problem is that they have too many and no way yet to determine which, if any, are correct. The singularity predicted by general relativity is not a physical object, it is a signal. It announces with mathematical clarity that the theory describing it has reached the limit of its validity. Just as Newtonian mechanics remains accurate for everyday speeds, but fails as velocities approach the speed of light, general relativity remains accurate for moderate gravitational fields, but fails where curvature becomes extreme. The singularity is the place where that failure occurs, and the theory needed to replace general relativity in this regime, the theory that would describe what actually happens at the center of a black hole, must be a theory of quantum gravity. Quantum gravity is not a single theory, it is a goal. It is the name given to the still unfinished project of unifying the two pillars of 20th century physics: general relativity, which describes gravity as the curvature of space-time, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales. Each theory on its own has been tested with extraordinary precision. General relativity predicts the bending of light, the precession of orbits, the dilation of time, and the existence of gravitational waves, all confirmed by observation. Quantum mechanics predicts the behavior of atoms, the structure of molecules, the emission spectra of stars, and the stability of matter itself, all confirmed with equal precision. But the two theories, as currently formulated, are fundamentally incompatible. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics treats the fundamental constituents of nature as discrete, probabilistic, and governed by uncertainty. When both theories are needed simultaneously, when gravity is strong and distances are small, as at the center of a black hole, neither theory can be trusted on its own, and no complete replacement has yet been confirmed. This is not for lack of effort. The search for quantum gravity has occupied some of the most talented physicists of the past several decades, producing frameworks of remarkable mathematical beauty and conceptual ambition. Two approaches in particular have shaped the discussion more than any others: string theory and loop quantum gravity. String theory proposes that the fundamental constituents of nature are not point-like particles, but tiny, one-dimensional objects, strings vibrating at different frequencies. Different vibrational patterns produce different particles, just as different vibrations of a guitar string produce different musical notes. The theory naturally incorporates gravity, predicting the existence of a massless spin, two-particle, the graviton, that mediates the gravitational force. In the framework of string theory, the singularity at the center of a black hole may be resolved because the fundamental strings have a finite size. They cannot be compressed to a point. The infinite density predicted by general relativity would be smeared out over a tiny but non-zero region, placing this singularity with something finite and in principle describable. String theory has produced important insights into black hole physics. In 1996, Andrew Strominger and Kamran Vafa used string theory to calculate the entropy of a specific type of black hole, a result that matched the prediction derived decades earlier by Jacob Bekenstein and Stephen Hawking, using very different methods. The Bekenstein-Hawking entropy formula states that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was a deeply puzzling result when first derived. Entropy, in thermodynamics, measures the number of microscopic configurations consistent with a system's macroscopic properties. For ordinary matter, entropy scales with volume. For black holes, it scales with surface area. Strominger and Vafa showed that string theory could reproduce this formula exactly by counting the microscopic string configurations that correspond to a given black hole. This was a powerful result the first time any approach to quantum gravity had provided a microscopic explanation for black hole entropy. String theory also gave rise to one of the most creative proposals for resolving the information paradox, the fuzzball conjecture. Proposed by Samir Mathur and collaborators beginning in the early 2000s, the fuzzball picture suggests that a black hole is not an empty region of space-time bounded by an event horizon with a singularity at the center. Instead, it is a ball of tangled strings and higher dimensional membranes, a fuzzball that fills the entire region up to where the event horizon would classically be. In this picture, there is no interior in the traditional sense. There is no empty space behind the horizon. There is no singularity. The entire black hole is a quantum object, and the information about everything that has ever fallen in is encoded in the detailed structure of the fuzzball. Hawking radiation in this framework is not thermal. It carries information because it is emitted from a structured surface rather than a featureless boundary. The information paradox in this view dissolves because information was never truly hidden. It was always part of the structure. The fuzzball conjecture remains controversial. It has been demonstrated convincingly only for certain highly specialized black holes in string theory, black holes with specific charges and symmetries that do not necessarily resemble the astrophysical black holes observed in nature. Whether the conjecture extends to realistic, rotating black holes in four-dimensional space-time remains an open question. Loop quantum gravity takes a fundamentally different approach. Rather than introducing new objects like strings, loop quantum gravity attempts to quantize space-time itself, to apply the principles of quantum mechanics directly to the geometry described by general relativity. In this framework, space-time is not a smooth continuum. At the smallest scales, it is woven from discrete units, tiny loops of gravitational field, linked together in a network called a spin network. Space, in this view, comes in finite chunks. There is a smallest possible volume and a smallest possible area determined by fundamental constants. Space-time is granular, not smooth, and the granularity becomes relevant precisely where general relativity predicts singularities. When loop quantum gravity is applied to the interior of a black hole, the singularity predicted by general relativity is typically replaced by a bounce. As matter collapses inward and densities approach the Planck scale, the scale at which quantum gravitational effects are expected to dominate the discrete structure of space-time, resists further compression. Instead of collapsing to infinite density, matter bounces outward, transitioning into an expanding region of space-time. Some models suggest that this bounce could connect the black hole interior to a white hole, a hypothetical time-reversed black hole, a region of space-time from which matter and light can emerge, but nothing can enter. The white hole hypothesis is speculative, but internally consistent within certain formulations of loop quantum gravity. In this picture, the collapse of a star does not end in a singularity. It passes through a quantum bounce, and the interior transitions over an extraordinarily long time, as measured by external clocks, into a white hole that eventually releases the matter and information that the black hole originally absorbed. The information paradox in this view is resolved by patience. Information is not destroyed, merely delayed, stored inside the quantum bounce until the black hole transitions into a white hole and releases it. These models are mathematically sophisticated and physically suggestive, but they remain unconfirmed. No experiment has yet probed the Planck scale. No observation has detected spin networks, fuzzballs, or quantum bounces. The proposals are theoretical frameworks, internally consistent mathematical structures that offer possible resolutions to known problems. But they await the kind of observational or experimental confirmation that would elevate them from promising ideas to established science. Other approaches to quantum gravity have produced their own perspectives on black hole interiors. Causal set theory, which models space-time as a discrete set of points connected by causal relationships, suggests that the continuum picture breaks down at small scales, and that singularities may not form. Asymptotic safety, which proposes that gravity remains well-behaved at all energy scales due to a special property of the gravitational coupling constant, offers another path to singularity resolution. Each approach brings its own mathematical tools, its own assumptions, and its own predictions, and each faces the same fundamental challenge: the absence, so far, of experimental evidence capable of distinguishing among them. This absence is not a failure of imagination or effort. It is a consequence of scale. The Planck length, the scale at which quantum gravitational effects are expected to become important, is approximately 1.6 times 10 to the negative 35 meters. This is roughly 20 orders of magnitude smaller than the diameter of a proton. No particle accelerator ever built, and none conceivable with current technology, can probe distances this small. The energy required to resolve Planck scale structures would be roughly a quadrillion times greater than the energy achieved by the Large Hadron Collider, the most powerful accelerator on Earth. Direct experimental tests of quantum gravity remain, for now, beyond technological reach. This does not mean progress is impossible. Indirect evidence may eventually constrain or support specific approaches. Observations of the cosmic microwave background, the afterglow of the Big Bang, may contain imprints of quantum gravitation effects from the earliest moments of the universe. Precision measurements of gravitational waves from black hole mergers may reveal deviations from general relativity's predictions that point toward quantum corrections. Advances in quantum computing and mathematical physics may enable new calculations that distinguish competing theories on theoretical grounds. And there is always the possibility of surprise, an observation no one anticipated, a measurement that reveals structure where none was expected, a signal from the vicinity of a black hole that carries information about conditions currently hidden from view. Science has a long history of such surprises, and the study of black holes has benefited from several of them already. What is clear, even in the absence of a final answer, is that the interior of a black hole is not simply a region of extreme gravity. It is a laboratory, a natural laboratory, inaccessible but real, where the two great theories of modern physics are forced into confrontation. Whatever happens at the center of a black hole, whatever replaces the singularity, whatever resolves the information paradox, will reveal something fundamental about the nature of space, time, matter, and reality itself. The answer, when it comes, will not merely explain black holes. It will reshape the understanding of the universe at its deepest level. The search continues, the mathematics deepens, the observations sharpen, and the question what happens inside remains one of the most beautiful unanswered questions in all of science. And so the question remains. After more than a century of theoretical work, after decades of observation, after the first images of black hole shadows and the first recordings of space-time rippling from black hole collisions, after proposals involving strings and loops and firewalls and fuzzballs and holographic boundaries, the interior of a black hole remains hidden. Not hidden by distance, not hidden by technology, hidden by the structure of space-time itself, by the geometry of a universe that permits a region from which no information escapes. This is not a failure of science. It is a signature of depth. The greatest questions in physics have always been the ones that resist easy answers, the ones that force existing theories to confront their own boundaries and reveal, in the process, something deeper about the nature of reality. The question of what happens inside a black hole is one of these questions. It sits at the intersection of every major framework in modern physics: general relativity, quantum mechanics, thermodynamics, information theory. It touches the meaning of space, the meaning of time, the meaning of matter, and the meaning of existence itself. And it remains open, not because scientists have failed to think carefully enough, but because the answer requires a kind of understanding that has not yet been achieved. What is known can be stated clearly: massive stars die. Their cores collapse. If the remaining mass exceeds a critical threshold, no known force can halt the compression, and a black hole forms. An event horizon appears a boundary defined not by any physical surface, but by the curvature of space-time, the point beyond which light itself cannot escape. Outside the horizon, general relativity has been tested and confirmed with extraordinary precision. The shadows cast by supermassive black holes match the predictions. The gravitational waves emitted by merging black holes match the waveforms calculated from Einstein's equations. The theory works. It works beautifully, consistently, and with a precision that leaves little room for doubt about the external geometry. Inside the horizon, general relativity continues to make predictions. It predicts that space and time exchange their roles, that all trajectories lead inward, that tidal forces grow without bound, and that the journey ends at a singularity, a point or ring, where curvature becomes infinite, and the equations cease to produce meaningful answers. For a non-rotating black hole, the singularity is a point. For a rotating black hole, it is a ring, surrounded by a richer geometric structure that includes multiple horizons, and, in the idealized mathematics, passages to other regions of space-time. But the singularity itself is almost certainly not physical. It is a marker, a place where the theory signals its own incompleteness. Most physicists expect that quantum effects, which are negligible at larger scales, become dominant as densities approach the Planck scale, modifying or replacing the singularity with something finite. What that something is, whether it is a quantum bounce, a fuzzball, a region of discrete space-time geometry, or something not yet imagined, remains the subject of active research and vigorous debate. The information paradox, sparked by Hawking's discovery that black holes radiate and eventually evaporate, has deepened the mystery further. If information is preserved, as most physicists now believe, then the event horizon may not be the featureless boundary that general relativity describes. It may carry structure. It may encode information. It may be, in some deep sense, a holographic surface on which the three-dimensional interior is written. The holographic principle, the AD-SCFT correspondence, and the firewall debate have all pushed the boundaries of understanding. But none has yet produced a complete, experimentally confirmed picture. What is most remarkable, perhaps, is how much has been learned about objects that cannot be directly observed through mathematics, through indirect observation, through the patient accumulation of theoretical insight. Scientists have constructed a detailed portrait of black holes, their formation, their external properties, their influence on surrounding matter, their role in galaxy formation and evolution. They have imaged their shadows. They have heard their collisions. They have measured their masses and spins with extraordinary precision. And they have identified with equal precision the exact boundary where current understanding ends. That boundary is not a wall. It is an invitation. It invites the next generation of physicists to develop the theory that unifies gravity and quantum mechanics. It invites the next generation of astronomers to design observations that probe ever closer to the event horizon, searching for deviations from general relativity's predictions that might reveal the fingerprints of quantum gravity. It invites the next generation of mathematicians to explore the structures that emerge when space-time is no longer smooth, no longer continuous, no longer described by the familiar geometry of Einstein's equations. The universe does not owe humanity simple answers. It does not arrange itself for easy understanding, but it does offer clues in the light, bent around a black hole's shadow, in the gravitational waves that carry the signature of colliding horizons, in the faint thermal glow that Hawking predicted but no instrument has yet detected, in the mathematical structures that emerge when brilliant minds push the equations further than anyone thought possible. These clues are enough to sustain the search. They are enough to suggest that the answer, when it comes, will be profound, not merely a technical correction to existing theory, but a fundamental revision of what space, time, and matter truly are. For now, the black hole keeps its secret. It holds its interior behind a boundary that no signal can cross, no telescope can penetrate, no instrument can reach. It sits quietly at the center of galaxies, at the endpoints of stellar collapse, at the intersection of the two greatest theories in physics, waiting for the theory that will finally describe what lies within. And perhaps that is fitting. The universe has always revealed itself slowly, reluctantly, one hard-won insight at a time. The nature of light took centuries to understand. The structure of the atom required the overthrow of classical intuition. The expansion of the universe was discovered barely a century ago. Each revelation came not from a single breakthrough, but from the gradual, patient accumulation of evidence, theory, observation, and understanding. The interior of a black hole will be no different. The answer will come. It will come through the same patient process that has carried science this far. Through curiosity, through rigor, through the willingness to follow the mathematics wherever it leads, even when it leads to places the human mind was never designed to imagine. Tonight, the black holes remain. They turn slowly in the darkness, unseen, unfelt, bending the light of distant stars around their hidden boundaries. They carry within them the compressed remains of dead stars, the accumulated matter of billions of years. And perhaps, if the theorists are right, the key to understanding the deepest structure of reality itself. They do not hurry. They do not demand attention. They simply exist, patient and silent, holding questions that the universe has not yet answered. And somewhere, in the quiet dark between the stars, the answers are waiting too.